Hello everyone, welcome back to another Intel Minds video. Today's video we're going to be talking about the area function and the antiderivative, which is a continuation of the integral lesson from last time. So let us begin by drawing out some function y equals f of x. Now let us declare this point as a and this point as b. And now let's declare this point as x and this rated region here, and let us declare some function a of x is equal to, this is an area function. This gives us the area of the shaded region. Right, so we want to find the area of the region bounded by f of x and the x-axis between a and b. So we can let a of x denote the area bound by f of x, the x-axis, and between a and x. Right, so the function a of x is the area function of f of x between a and b. So it allows us to find the area between a and b. And as x increases, a of x also increases. So let us try to find a prime of x. I'll begin with an example here. So let's find the area function a of x for f of x equals to 2x minus 1 on the interval 1 to 2, right? And let us also find a of 1 and a of 2, right? So, and let's interpret the results. Let's first draw out the function here. It's going to be given to us like so. And this is going to let us declare this point as 1. This point is a half. And declare this point here. Just make these solid lines for easy to read. And this is some point x, and this is some point 2. So if we declare this point as x, this point is obviously going to be x, and the y value will be 2x minus 1. This point here will just be 1, 1, as seen given by our function. Right, so we're trying to find this region here, right, the shaded region here, and we need to think of some area function a of x to denote this area. So we have a note here that a of x is a trapezoid. So that we can write a of x is equal to base 1 plus base 2 over 2 times height. Exactly what we're going to do here. We're going to find base 1. Let's just treat this side here as base 1. This side here is base 2. We're going to get 1 plus 2x minus 1 over 2 times the height, which is going to be the difference here, which we're going to denote as x minus 1, given to us by this region here, this difference here, right? And now if we just simplify this a little bit, now this will go away, this will go away, this will go away. We're just going to get x multiplied by x minus 1 and get x squared minus x. All right, so we can prove this and ensure this is the correct function. If we just find, let's find the area of the area at 1, which is going to equal to 0. 1 squared minus 1 is 0. And this is in agreement with the diagram because this area function allows us to find the area between 1 and 2, or 1 and 2, and it allows us to find the area between 1 and x. So if we put in 1 for our value, we're going to find the area at 1. So from 1 to 1, which is going to be 0, which is just a straight line, it's going to be no area. And look, if we substitute the value for 2, we're going to get 2 squared minus 2, which is going to be 2, which is going to be the area from 1 to 2, as given by our area function, 2 square units. And if we try to find a prime of x, we'll realize that a prime of x is actually pretty simple. Just give us 2x minus 1 as given here, x squared minus x, the derivative of that. And we can realize that a prime of x is actually equivalent to f of x. A little bit odd, is that not? And something you have to understand here is that this holds true for any positive continuous function f of x, holds for any positive continuous function, right? So as x increases, you realize that the area bounded by f of x and the x-axis from a to x increases at a rate equal to the value of the function at position x. All right, so how do we prove this? So let's just let f of x be some positive continuous function, right? Between a and b, right? And let's let a of x be the area function, right? So a of x denotes the function on this interval. And so let's just draw out some arbitrary function here with intervals a and interval b. Let's have these two intervals here, x and x plus some arbitrary number h. And this is the shaded region that we want to find. And so we know that this will be found using the area function of x plus h minus a of x. If you look at it, this shaded region here is actually all of the area to the left of it subtracted by all the region area left of a of x, right? So if you consider the change in a of x from x to x plus h, since a of x plus h is the area from a, right, from the area from a to x plus h, if a of x plus h is this area, right, all this shaded region here, and a of x is all of this region here, then we'll realize that this here, a of x plus h minus a of x is equivalent to, let's declare this as some rectangle here with some point here. Let's give that the point c of and f of c. And this is going to be equivalent to this rectangle. Let's say some very small rectangle. I'll give you guys a zoom in, just to better understand this. We just zoom in very far into this point C. This very, very, very small point here of C and f of c, f of c. We're going to realize that this is just some shaded region equals to this area of this rectangle. Let's just let that be true, that the shaded region on the left diagram is equivalent to this this shaded rectangle here with height fc, right? So this equation over here is equivalent to hf of c, right? Which h is just this distance here. This is h. All right, and then we can rewrite this as f of c is equivalent to the area of x plus h minus a of x divided by the difference that is h. And so forth. We can find that the a prime of x is equivalent to the limit of h approaches to 0 by definition of the derivative of a as x plus h minus a of x over h, right? This can give us a limit as h approaches 0 of, replaces f of c. You replace, remember, from this equation right here, you're going to replace this entire part. And this is going to be now replaced with limit as c approaches x for f of c. And this is just equal to f of x, since f of x is since f of x is continuous. So this basically just means that as it approaches x and is continuous, so it is just equivalent. So the derivative of the area function is equivalent to the function itself. So there is the proof for that. All right, and now let's do a quick example to wrap this up. So find the area function for f of x is equal to x squared plus 1 on the bounds of 1, 2, 3. Right? And then also calculate region between y equals x squared plus 1 and the x-axis on 1 x to 3. So first we're going to find the area function. All right, so remember that the derivative of the area function, is equal to the function itself from what we just discussed. And so that means the derivative of the area function is equal to x squared plus 1. And now we can take the integral of this, integrate this, and you know that the a of x is equal to a third of x cubed plus x plus our constant, integral constants here. And now we have to find this c in order to find what our area function actually is, right? So we use the fact that a of 1 is equivalent to 0. Remember that? Since our area function is on the interval 1 to 3, we know that the area at 1 at the beginning of the interval is going to be 0. And now we're going to substitute that in. We're going to 0 is equal to 1/3 cubed plus 1 plus c. Solving this, we're going to further get c is equal to -4/3. Right? Move the 1 over, it's going to be a -1. Move the -1/3 over, that's going to be -4/3. Thus, we get our area function is going to be equal to a third x cubed plus x minus 4/3. And now we just need to find the region between between 1 and 3. So we can just basically, since our area function is on the interval of 1 to 3, as we substituted 1 for 0, we can just substitute in 3. And this will give us the area from 1 to 3. And this should be pretty self-explanatory here. Just do the math, work through it. You're eventually going to get 12 minus 4/3. And this is just going to be equal to a 36 minus 4/3, which is going to equal to 32/3. And that is how you use the area function to find the area between 2 points.